in real time. We used a shared memory architecture internally to the programs. We did this to by having an off-board computer and an on-board computer. Basically what we did was we copied the shared memory, so we have identical copies on both a PC and the local computer. By doing this, it lets us run certain algorithms off-board and pipe that information in very quickly and easily, basically transparently, in order to allow for example, if we wanted to run SLAM off-board or if we wanted to do stereo vision off-board, the 802.11n gives us the bandwidth that we need to be able to pipe all that data off-board, and then heavy computations can be run on another computer and can then be sent over to the gumstick without it having to do too much overhead. Another piece that we, like I mentioned earlier, we were looking at reconfigurability as a key point of our vehicle. So we created mission scripts where it's able to call different functions at different points without having to recompile the software. We felt this was important from a user interface point of view. If somebody is going to use something in a real scenario, this is something that would have to be there, because you don't have programmers on site with emergency personnel usually in order to change a vehicle and its mission. And here's a screenshot of our GTK software with IMU information on it, as well as we were able to, in real time, update our PID constants and had very close and fine-tuned control over the vehicle at all times. And yet it was still running everything locally on the gumstick, so there was no latency except for, updating gains and items like that. For risk reduction, the motors are held in reset whenever the Zigbee kill switch is activated. The shroud protects both the vehicle and bystanders from damage. We chose to go the entire perimeter around the vehicle, which we felt would aid us if we had close circles around each propeller. We felt that there was some probability of it getting caught on doorways or windows as it goes through. So with the parallel shrouding, we felt that as we went through a window or other apertures, we would be able to slide through rather than hook and spin us. We also shielded sensitive communication lines from inductive noise to avoid erroneous operation. And also the motor controllers disable after 500 milliseconds if they haven't heard anything from the gumstick. So if it locks up or resets, you don't have the vehicle in its last state flying off into the sunset. It will die and set down. And just our progression, we really came from a lot from not really having any program to start with. It was all initiated from undergraduate students, and we've learned a lot as we've come along, and we've really enjoyed this competition, and it's been a great challenge for all of us. And like I mentioned earlier, our budget included our lab setup costs and things like that, so we were a little bit strapped in, especially in this economy, but we started very basic, and this was one point that we wanted to bring out, was that we started with just a teeter-totter with 2 motors on it, put the IMU on it, and got a good handle of what a PID loop is, and then we cut and pasted it into two axes and had a four-axis set, or 3-axis setup, and then we progressed from that up to our vehicle. So going in stages really helped our development and improved our ability to nail down errors at later points, because we didn't have to troubleshoot the entire vehicle all at once.
It also allowed us to kind of incrementally develop our knowledge about flight control systems, because this is all new to our group. And so all of our platforms were fixed to certain axes until we were able to have a fully pivoting system balancing, so that we had some level of confidence that when we went to a tetherless platform, we'd have some kind of a stable flight platform. And we did that, and we didn't have to deal with crashing vehicles or anything like that during the development of this, which for our team was, budget-wise and whatnot, a huge constraint. So that strategy worked well for us.
Just in conclusion, the highlights that we really found was most useful about our approach was that the bidirectional memory sharing improved the ability to debug and control the vehicle, particularly during testing, the testing phase of the vehicle. And it also enabled us to be able to easily expand it with computationally intensive offboard processes. The scripting of calling functions also allows for modularity and ease of configurability by end users. They don't need to be programmers in order to be able to use our vehicle.